Thank you for watching for this video. This is Shunsuke Aoki, a researcher at Carnegie Mellon University, and the work is collaborated with General Motors Company. The talk title is Co-Simulation Platform for Developing InfoRich Energy-Efficient Connected and Automated Vehicles, and this talk is for IEEE Intelligent Vehicles Symposium in 2020. In this talk, we present a co-simulation test platform and eco-autonomous driving strategies for saving fuel. Let me start from the motivation first. According to the US Energy Information Administration, over 150 billion gallons of fuel are consumed in the US every year, and over 30% of US energy-related CO2 emissions come from these ground vehicles. In fact, each country and many companies are trying to reduce the CO2 gas emission. At the same time, connected and automated vehicles, which is also called CAVs, CAV, or self-driving vehicles are rapidly studied, and we expect a variety of energy-saving applications such as intersection connectivity, platooning, and eco-driving strategies. For example, if vehicles get the traffic light information before approaching to the intersection, by using intersection connectivity and vehicular communications, the vehicle is able to save energy. Based on these applications, automated vehicles have the great potential to improve fuel efficiency. In fact, as a part of the US DOE, Department of Energy, ARPA-E Next Car program, General Motors and Carnegie Mellon University design and develop InfoRich eco-autonomous driving strategies, which include eco-approach, eco-departure, and eco-cruise. For example, in eco-approach, as shown in this figure, when the vehicles know the stop in advance, the vehicle can proactively engage in coasting and saving the fuel energy. By incorporating static and dynamic data, including map database, preloaded vehicle data, onboard sensors, and V2X vehicle-to-everything communications. For example, by using map database, the vehicles always know the grade and curvature for the upcoming trajectory and determine the behaviors based on it. However, to design and develop eco-driving technologies for cabs, self-driving vehicles, test and verification are very important, but at the same time, very difficult due to safety, cost, and repeatability. For example, misbehavior on public roads is able to lead to vehicle collisions or accidents. Also, cabs experiments spend much time and human resources. In addition, traffic situations on public roads keep changing in the real world, and that is why comprehensive study may be difficult. Therefore, in this work, we design and develop realistic simulation environments that provide realistic road networks and realistic traffic. Here is our outline of this talk. We have already covered our motivation and InfoRich eco-autonomous driving strategies. We present the co-simulation architecture next. And after that, we present the real-world driving scenarios, including synthetic drives and map tools for the co-simulation platform. First of all, co-simulation is a promising technique to model complex and dynamic systems in a distributed manner and to simulate by each subcomponent without being aware of the entire system. Let me introduce our co-simulation platform here. To test and design the eco-autonomous driving strategies, we developed the co-simulation platform that includes traffic environment simulator, eco-autonomous driving systems, which is named IRED, InfoRich Eco-Autonomous Driving System, and Simulink-based vehicle model. Here, map database provides a realistic road networks for traffic simulator and IRED autonomous driving system. The traffic simulator provides a sensor model, traffic model, static objects, and traffic light information. The IRED system is a hybrid emulator simulator for autonomous driving systems, and we can implement eco-driving applications on it. Also, the Simulink model provides realistic powertrain model and vehicle dynamics model. By replacing this Simulink model with the vehicle hardware, we also use the platform for hardware in the loop test. These three software run simultaneously and keep exchanging data by the UDP protocol. Let us see how it works. Again, traffic simulator provides static and dynamic obstacles on the simulation board, and the eco-autonomous driving system power system for planning and navigation. Here, we show the static obstacles and moving obstacle in the traffic simulator. The Ego vehicles has onboard sensors to capture these surrounding objects. These information are processed and transmitted at 50 Hz to eco-autonomous driving system. As you can see in the right figures, the autonomous driving system processes the static and moving obstacles. Likewise, traffic signal informations are also generated in traffic simulator and used in eco-autonomous driving system. In addition to that, in the co-simulation platform, Simulink provides vehicle dynamics and powertrain model as shown in the figures. That includes engine model, transmission model, and vehicle body model. Also, our system includes a variety of vehicle-specific tables, such as torque speed tables and fuel tables. This lookup tables tells you how much fuel might be consumed at the given speed and the given acceleration. By using these lookup tables, our autonomous driving systems determine the future behavior and speed trajectory. Let's move to the another topic, real-world driving scenarios. To test and verify our eco-autonomous driving strategies, we use the realistic driving scenarios from real-world driving data. First, we use the synthetic drive cycles provided from National Renewable Energy Lab, NREL, to get the real-world driving data, which includes a variety of information, such as grade, curvature, intersections, speed limit, and traffic controllers. However, the synthetic drives are pre-processed for privacy concerns and represented in CSV table format like the right figure. Therefore, we develop an auto parser and calculator for map and scenario, which is named Auto Pascal, to reconstruct the load networks from the synthetic cycles. This tool provides the map and scenario files for traffic simulator and for eco-autonomous driving system, IDED. Here is one example for load networks. By using the data in synthetic cycles data, Auto Pascal processes and generates the load networks. Traffic light information and turn direction information are used for determining the location for intersections, and also each road segment can be developed with curvature and grade information. Let's see driving scenarios used in co-simulation platform. Since the traffic simulator and the eco-autonomous driving system use different map format, AutoPascal has two-step file generation like this. AutoPascal firstly generates open drive and open scenario file for traffic simulator, and then convert them into RNDF and MDF files for eco-autonomous driving system. By using the map generation tool, we can get these consistent maps for traffic simulator and eco-autonomous driving system. Both load networks are developed exactly same in the different format. They are including grade and curvature information, and our eco-autonomous driving strategies account for the grade and curvature to save fuel consumption. This is demo video. The left side UI is IDED eco-autonomous driving systems, and right one is traffic simulator. Here, traffic controllers, static obstacles, and traffic, which means moving obstacles, are generated in right side traffic simulator, and the left side eco-autonomous driving system subscribes these information for planning and determining its behaviors. These two software runs simultaneously and keep exchanging the data between them. Here is a concise evaluation for baseline driver with and without traffic. Since this is a test for simulation environment itself, we didn't evaluate the eco-driving strategies here. Here is the fuel consumption results for one travel, which is around 1.6 kilometers. X-axis describes the trip distance and y-axis represents the consumed fuel. Blue line is the performance without traffic and orange brake line is with traffic. Due to the traffic, the target vehicle spent additional fuel here. Also, here is the fuel rate per second. Here, y-axis describes the fuel rate. For evaluation, we use the vehicle models that are provided from General Motors. From these results, we can say that the co-simulation is able to evaluate fuel consumption in a variety of traffic models and different volumes. To wrap up, in this talk, we presented the co-simulation test platform to test, verify, and validate energy-efficient driving strategies for eco-autonomous connected and automated vehicles. Also, to run the simulation in realistic driving scenarios, we presented the synthetic scenarios and map tools named AutoPascal to parse and reconstruct the road networks from driving data. Finally, we showed the demo video and evaluation for the co-simulation and showed that our platform is able to safely and cost-effectively evaluate fuel consumption in a repeatable manner. Based on the practical co-simulation platform, we will design a variety of eco-driving technologies for connected and autonomous vehicles. Thank you very much for seeing this video for IEEE Intelligent Vehicle Symposium 2020. Please feel free to contact us for any questions and feedback.